In this lesson, we'll be talking about how to interpret slope fields. So solutions to differential equations can be considered either general or particular. When given a slope field and a point, we can sketch a particular solution. We can also draw conclusions about the original equation. So let's take a look at this first slope field here and see if we could draw any conclusions about the original equation. So I like to think about it a bit as like connecting the dots. So I'm going to start at the origin here, and I'm going to go towards the left. And I can kind of see like, okay, well, those follow the trend. And if I keep going, now it looks like I'm going upward. Now it looks like I'm going down and back up. And if I go over to the right of the y-axis, I can kind of follow that same trend. And I see that I kind of have this wave pattern here. So by looking at this, I could draw a conclusion that the original equation represents sine. So we don't know exactly what the equation is, but we can tell that this is definitely a sine curve here in this first example. Whereas in the second example, this one might be even easier to see. If I start kind of connecting these little slopes, we form basically all of these circles. Now each of these represent a general solution. When we put this all together and we have a specific point, then we can pick one of these and we can say, okay, that's the particular solution. So here I could say that the original equation is a circle. All right, let's look at some other examples of interpreting slope fields. Number 1 says, given the slope field below, sketch a graph of the particular solution that includes 0, 1. So again, the slope field represents all of the solutions, the general solution to a differential equation. We want to sketch a particular one here. So it tells us we want to go through the point 0, 1. So I'm going to start by plotting a point at 0, 1. And then I'm going to see if I could kind of connect some of the little slopes around it in order to form a sketch of the particular solution. So to me, my instinct is to connect these and then go back up this way. Okay, you might be able to tell in this case that the original equation is a hyperbola. We could see that it basically looks symmetric over the x-axis here. All right, and number 2, we're going to sketch a graph of the particular solution that includes 1, 6. So if I plot the point 1, 6, I'm now going to connect some of the surrounding slopes, and I want to make sure that it goes through 1, 6. And I can tell here definitely the graph of this original function has to be exponential by the way this slope field looks. Number 3, a slope field is given to the right. For part A, we're going to sketch a particular solution that includes 5, 0. So I'm going to plot 5, 0. And I know when doing a particular solution, you might not know exactly which slopes to connect. So for instance, maybe on that question, you are going to make yours a lot flatter. Okay, as long as we're connecting surrounding slopes and we're going through that particular point, that is a particular solution. In this case, which function family does the solution belong to? Well, we already looked at a sine curve in this video, so this is definitely not sine. We've also looked at choice 3, exponential, and this does not represent that. Quadratic would be like a parabola, and I don't see that U-shaped curve here. So this represents logarithmic or potentially natural log in terms of the function families. Number 4, this is a really common question of how interpreting slope fields can be asked in a multiple choice format. So particularly if this was, let's say, the AP Calculus exam, they might have 4 answer choices here, and you have to pick which slope field represents this differential equation. So it tells us that dy dx is equal to x plus y. So basically the slope fields have been sketched for us, so we have to see which one represents x plus y. The quickest way to go about this is to look at each slope field in each of the answer choices and find the slopes that are 0. So if I take a look at choice A, I see all of these little horizontal lines, which mean the slope is 0. Okay, if I look at B, I see the same thing, but they're kind of going upwards. And you certainly don't need to highlight all of them. I'm just pointing them out to you here in this video. And then in C, same idea as that last one. The reason I'm doing that is because when we look at a slope of 1 or 2 or 3, sometimes we can't identify it clearly, but we can definitely look at a slope field and identify a slope of 0. So we now want to pick one of those points and see if it makes the statement true. So let's say I go to A and I pick this point here that I'm bolding. Okay, so that point is 2, -2. If I add those together, so 2 plus -2, I do get 0. And we know there the slope, dy dx, is equal to 0. So I see that works. If I try that in choice B or C, you will see that will not work and we will not get 0 as our slope. So the answer for is choice A. All right, and for our last question, in which quadrants is the differential equation dy dx equal to x squared over y cubed, always positive? So remember our quadrants, we start on the top right and we go around counterclockwise. And then let's look at this dy dx, this differential equation they give us. We could say that the numerator is always positive, right? When we square a number, we're always going to get a positive back. So really what matters is we want y cubed to be positive. So if we take a look at this, the quadrants in which y to the third power would be positive, that would be whenever y is positive, and that would be quadrants 1 and 2.